Hey guys, what's up? Hopefully things are going well so far this week. The exams have been graded. They were graded Sunday. Dr. Ming and I were having a little discussion as of yesterday still. So the average is right around 70. So that's pretty average. Way to go. Hopefully we can. I'll get those up today, no problem online. What I'll do actually is share a folder with you that has all of your graded material in it, and that way you can kind of see feedback and just have like direct access to your exam even while it's being graded, and that way you can know when it's graded or whatever. So I have to set that up, but yeah, that's what I'll do, is set up a folder with all your information and all your exams and stuff in it. That way you can see when they're graded, because we're just grading them virtually basically. Like I have a tablet, Dr. Ming has a tablet, and we can just grade them directly after we download them from Moodle. So, but yeah, they're done. Don't worry, we'll get them up today. I'm sure Dr. Ming posted his already yesterday probably. But anyway, just a heads up, they're done. I know everybody's been patiently waiting, and I appreciate that. So yeah, we'll kick back off today with some more method of undetermined coefficients, and then get into a different method for non-homogeneous equations called variation of parameters. So the method of undetermined coefficients we talked about, we started that last time. And we're basically solving this linear non-homogeneous equation, A in constant coefficient, right? Constant coefficient y nth derivative plus dot 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 a1y prime plus a0y equals g of x. And we said the first thing that we need to do was solve for the homogeneous solution, y sub h of x. Next thing was to guess yp of x form. And the next thing was to substitute yp and its derivatives into the left-hand side of the non-homogeneous equation. Next thing is to solve for the coefficients. Solve for the coefficients in yp, and then form the general solution y of x equals y sub c or y sub h plus y sub p. So those were our steps that we kind of introduced last time for non-homogeneous equations. And yeah, let's look at another example. And this example is going to kind of break everything that we already know. So example, basically we want to solve, meaning find a general solution. To the differential equation y double prime minus 5y prime plus 4y equals 8 e to the x. So it's kind of just a recap, and it's going to show us something that can happen. So the solution, well, first thing we do is we solve the corresponding homogeneous equation. So first, solve y double prime minus 5y prime plus 4y equals 0 to get y sub h of x. So first I want to get the corresponding homogeneous solution. Well, that means m squared minus 5m plus 4 equals 0. We can factor that. That's m minus 1 m minus 4. So that's m equals 1, m equals 4. So then that tells us y sub h is going to equal c1 e to the x plus c2 e to the 4x. So that's like our y1 and our y2. So here's our y1 of x, and here's our y2 of x. So c1 y1 plus c2 y2. Now let's guess our yp. So for our yp, we guess it based on the form of g of x. So we guess yp of x equals, well, we have to base our guess on the form of g of x. So g of x over here is constant times e to the x. So normally we would guess yp equals constant a times e to the x. Right, that's our guess for the method of undetermined coefficients. So then that would mean yp prime will be equal to a e to the x, and yp double prime be equal to a e to the x. And now substitute those into the non-homogeneous equation. So we get a e to the x minus 5a e to the x plus 4a e to the x equals 8 e to the x, and solve for a. So that on the left, we could factor out e to the x, and that leaves us with a minus 5a plus 4a equals 8 e to the x, and the e to the x's can cancel. And so on the left, I've actually got 0 equals 8, 0a equals 8, question mark. What's happening? What is happening? We just, like, everything broke. So this is a problem. This is a big problem. But why is it a problem? Because our guess from the chart that I gave you last time, this guess is actually already part of our homogeneous solution right here. Constant times e to the x duplicates term in YH. So that is a problem. When our guess from our chart duplicates our homogeneous solution, that means it's going to give us a 0 on the left because it's a homogeneous solution. So what we have to do is we have to eliminate the duplication. So the way to resolve this, we multiply our initial guess by x to the n, where n is the smallest power that eliminates the duplication. So basically, in this example, it'd basically just be n equals 1. N equals 1 for this example. But it could be like n equals 2 if you had a repeated root in your homogeneous solution. So it just depends on the homogeneous solution. So, and when we say smallest power, we mean smallest integer power, positive integer power. So positive integer power. That eliminates the duplication. So what we're going to guess is not yp equals a e to the x. We're going to guess, so we should guess yp is actually a times x e to the x. And now that is a linearly independent function from our homogeneous stuff. So we basically want all linearly independent terms, because if it's duplicating a term in our homogeneous solution, because it's not linearly independent, then that's going to give us 0 on the left. Now what do? We take the derivatives. So yp prime, little product rule, so a times e to the x plus a x e to the x, and then yp double prime is going to be a e to the x plus a e to the x plus a x e to the x, which is really just 2a e to the x plus a x e to the x, yp double prime. Now substitute those into the left-hand side of the differential equation, and if I remember correctly, it was y double prime minus 5y prime plus 4y. So that's going to be 2a e to the x plus a x e to the x minus 5 times a e to the x plus a x e to the x minus 4a x e to the x equals, on the right hand side we just had 8 e to the x. And on the left we can factor out e to the x, so we'll do that. E to the x comes out. That gives us 2a plus ax minus 5a minus 5ax minus 4ax equals 8 e to the x. And we can cancel the e to the x now. It's never 0. We can simplify. Let's simplify the left-hand side to give us, I think that's like negative 3a, and then the ax e to the x actually cancels. Or sorry, the ax times the coefficients, those all add up. So negative 3 equals 8, basically. And that tells us that a is going to be negative 8 over 3. So that is going to be our homogeneous, or sorry, our particular solution. So this implies that yp of x is equal to negative 8/3 x e to the x. And that is our particular solution. So particular solution to the non-homogeneous equation. And so the general solution is y of x equals c1 e to the x plus c2 e to the 4x minus 8/3 x e to the x. And that's it. 4 should, yes, thank you. 4 should be positive here. And then it cancels. Thank you. So let's, our first example, basically we just have to eliminate the duplication. So that's the key. Let me go up and highlight that. So this box right here is how we handle whenever we have a duplication in our guess from the chart. We don't use that guess, we multiply by x until we've eliminated all duplications in our homogeneous solution. In this case, we just had to multiply by x one time, but you might have to multiply by x squared, or you might have to multiply by x cubed, depending on how many repeated roots you have from your non-homogeneous, or sorry, from your homogeneous solution. So yeah, good stuff. Let's see, one thing I want to point out is if you need to solve for C1 and C2, you cannot do that. So note, we cannot find C1 and C2 until we've formed the general solution. Right, because the initial conditions are for y of x0 equals y0 and y prime of x0 equals y1. Like, these values apply to the general function, not just the homogeneous solution. So these conditions apply to the general solution. These apply to y of x, not yh of x. So very important, if you do have initial conditions, you can solve for C1 and C2, but you have to do it after you have added the particular solution, because those initial conditions are applying to the function y, not the homogeneous solution. Okay, so let's look at another example here. So another example. Let's see. Find the form for yp of x. So find the form of yp of x. Don't necessarily solve for the coefficients, but just find the form. And the differential equation is fourth derivative of y plus y triple prime equals 1 minus x squared e to the negative x. So this is our non-homogeneous differential equation. Note here we have like a G1 and a G2. So we're actually going to need two pieces to our YP, our particular solution. So solution, first, what do we have to do? First we solve the homogeneous equation, y4, so fourth derivative, plus y triple prime equals 0. So that would be m to the 4 plus m cubed equals 0. And I can factor as m cubed times, m cubed times m plus 1 equals 0. All right, so let's see, that's going to be m equals 0, multiplicity 3, m equals negative 1, it's multiplicity 1. So that tells us our homogeneous solution is going to be, let's see, C1 e to the 0 x plus C2 x e to the 0 x plus C3 x squared e to the 0 x plus C4, my favorite, e to the negative x. And we don't write it that way. We want to plug in, those zeros. So that's going to be C1 plus C2 x plus C3 x squared plus C4, my favorite, e to the negative x. That's our homogeneous solution. Now, normally we'd guess yp of x equals, well, for the first function, g1, normally we would just guess a constant, a. But that's not good enough, right? We already have a constant right here, c1. So maybe I should multiply a by x. It's a constant times x. Well, I already have that as well, c2 times x. Well, maybe I should make it x squared. Well, constant times x squared, I already have that as well. So actually what we need to do is make it constant, a times x cubed. And this eliminates duplication from YH. So that is good to go. Plus, let's see, we have, normally, what do? We would say ax squared plus bx plus c times e to the negative x. Because we have a quadratic, g2, x squared e to the negative x. So the general form of a quadratic would be ax squared plus bx plus c. However, that, again, duplicates constant times e to the negative x, constant times e to the negative x. So what we have to do is multiply this by x. And that is going to be the general form of our particular solution. And actually, I don't want to use a again, do I? I want to use something else, like, I don't know, we'll use e. I don't want to have two a's, like, that's bad. Mentally, it's bad. It's not really bad. Just keeping track of which a is which, that would be tough. But yeah, that's it. That's our our particular solution. And then I would need to find all four of those constants, form the general solution, and then solve for C1 and C2 if I had some initial conditions or something like that. So could be a little tedious, but just hang in there. I think it'll be okay. So let's see, any questions? I'll do one initial value problem and then we'll move on to the next section. So example, solve the IVP. And that is going to be, let's see, differential equation y double prime plus y equals 10 sine x. And y of pi equals 0, y prime of pi equals 2. So, solution. We have to find the corresponding homogeneous solution. So m squared plus 1, m squared plus 1 equals 0. So that tells me m is equal to plus or minus I. So that's alpha equals 0, beta equals 1. So our homogeneous solution YH is going to be C1 cosine x plus C2 sine x. So that is our homogeneous solution. Now what would we guess for our particular solution? Yp of x, normally, based on the right-hand side, g of x over here, this is our g of x. Normally we would guess a times cosine plus b times sine. But that's not good enough because we already have that in our homogeneous solution. So this duplicates our homogeneous solution. So what we need to do is multiply this guess by x. So this guess gets multiplied by x. And so this eliminates duplications. And then we have to calculate yp prime. So yp prime is going to be product rule. Let me factor this actually. Let me say this is x times a cosine plus b sine. That's probably the way I should have written it anyway. Now that'll make the product rule a little bit easier to do. So this is going to be product rule, derivative of the first would be 1, so then multiply a cosine x plus b sine x plus x times a negative sine x plus b cosine x. And that is our first derivative. Now what's yp double prime? So yp double prime is going to equal negative a sine x plus b cosine x plus, now this is negative a sine x minus, or sorry, plus b cosine x plus x times negative a cosine minus b sine x. Just doing a product rule again on the second half of that. And now I'll combine that yp double prime to give me negative 2a sine x plus 2b cosine x minus ax cosine x minus bx sine x. That's yp double prime. And now I need to take those and substitute them into the left-hand side of the non-homogeneous equation. So substitute, sub these into the non-homogeneous equation. And so we'll get yp double prime plus y equals, or yp equals 10 sine x. So that's going to be negative 2a sine x plus 2b cosine x minus ax cosine x minus bx sine x. So that's yp double prime plus yp is going to be ax cosine plus bx sine equals 10 sine x. Right, this first one, that's yp double prime, and the second one, that's just yp. And the right hand side is our g of x. That's g of x over here. So that is our differential equation with our particular solution substituted in. And now it looks like we have some nice cancellations. Negative ax cosine x, positive ax cosine x. Negative bx sine x, positive bx sine x. So then we really just get the equation negative 2a sine x minus 2b cosine x equals 10 sine x. And now what can we do? We can equate the coefficients on the left and the right in front of the linearly independent functions. So that's basically going to be negative 2a equals 10 and negative 2b equals 0, because the coefficient of cosine is basically 0 on the right hand side. So that's all coming from linear independence, honestly, but see, a then is going to be negative 5 and b is going to be 0. So our particular solution, yp of x, should be equal to, let's see, negative 5x cosine x. And our general solution, y of x, should be equal to c1 cosine plus c2 sine minus 5x cosine x. So that's our general solution, but we have initial conditions. What are they? They're y of pi is equal to 0 and y prime of pi was equal to 2. So let's solve for C1 and C2. Positive, yeah, sorry. It should be positive 2b cosine x. Thank you. We still get b equals 0, but yes, should be 2. Positive 2b. Thanks. Let's see. Now, y of pi equals 0 means c1 cosine of pi plus c2 sine of pi minus 5 pi cosine of pi. So let's see, sine of pi, that's 0. Cosine of pi is -1, and cosine of pi is -1. So what is this going to tell us? This is going to tell us that 0 is equal to negative c1 plus 5 pi. So that tells us that c1 is actually equal to 5 pi. Right, so then we plug that in. I'm going to erase right here, put a 5 pi right there. And then I'll take y prime of x. So what is y prime of x? It's going to be negative 5 pi sine x plus c2 cosine minus 5x. Minus 5 cosine. I should put that whole thing in parentheses to keep the minus sign outside. So 5 cosine minus 5x sine x. And now y prime of pi should be 2. So y prime of pi equals 2. That's going to be negative 5 pi times sine of pi plus c2 cosine of pi minus 5 cosine of pi plus 5 pi sine of pi. And we know sine of pi is 0, so these go away. This is -1, this is -1. So what are we going to get? Let's see. We get 2 is equal to c2 times -1 plus 5. So you can get c2 equals 3. c2 equals 3. So our general solution, y of x, is equal to 5 pi cosine x plus 3 sine x minus 5x cosine x. And that is our unique solution to this non-homogeneous equation. So it's just a little tedious. Hang in there. Build up your endurance. It's not going to be too bad. You just got to be careful. Take your time. Don't rush through it. Oh, well, we'll be done. I guess we'll finish that. That'll be our last thing in method of undetermined coefficients. Unless there are any equations, we'll move on in just a minute. Take a breather, catch our breath. Any questions? Sweet. Good stuff. All right, let's move on to variation of parameters. So this is the next section for us, 4.6. So 4.6 is the variation of parameters. And this is a very common solution technique in differential equations. That's actually how you derive the integrating factor. But we're not going to do that derivation from chapter 2. We're going to just do this derivation here in chapter 4. But before we do that, I want to remind you of something called Cramer's rule. So first recall Cramer's rule. Cramer's rule. And I know that like most people, when they hear that word like review or recall, it's usually like, what are you talking about? I never went over that ever. So I know it's like naive to say that, but I don't think it's too hard for you to pick up on the fly, to be honest. So if you've never seen this before, it shouldn't be a big deal. But it's basically just a way to solve a 2x2 system of equations. So it really just uses determinants. So we use determinants to solve systems of equations. And the system of equations could be something like ax plus by equals m, or the next equation, cx plus dy. D is a bad word, or bad letter. cdey equals n. So provided the system can be solved, basically saying AD minus BC equals, or is not equal to 0. Basically the determinant of the left coefficient matrix would be non-zero. Then Cramer's rule says that x is equal to the determinant mn be over abce, and y is equal to amcn over abce. So it's a quick way to solve a system of if it's small. If it's a really small system, it's a quick way. If it's a big system of equations, like 10 equations, 10 unknowns, it's definitely like probably the most inefficient way to solve it. But if it's a small system and you're doing it by hand, it's pretty easy to do, especially 2x2. So yeah, that's Cramer's rule. So we'll need that at some point in our derivation of the variation of parameters particular solution. So just to throw that out there. Hopefully that's not too hard for you to understand. And I think you should have seen it before, especially if you had like pre-calculus or something like that here. I'm pretty sure everybody should be covering that, or did cover it at one point. So does that make sense? Okay, great. Now, in this section, variation of parameters 4.6, what we're going to do is we're going to focus. So we will focus on the second order linear differential equation with or without constant coefficients. So this is really a more general method than method of undetermined coefficients. So it could be non-constant coefficients, unlike 4.4 where we had method of undetermined coefficients that had to be constant coefficient. This is going to be a more general method. So basically the differential equation, we can write a L of y, right, our linear operator. Well, we can write that as y double prime plus, we'll call it p of t, y prime plus q of ty equals g of t. So this is our linear non-homogeneous differential equation, possibly without constant coefficients, but it's in standard form. Note, this is standard form. Note, standard form, since coefficient of y double prime is 1. If it's not 1, you have to divide by that coefficient first. So if it's not 1, you first divide by that coefficient. Well, we have our standard form differential equation. Now, suppose we have y sub h of t is equal to c1 y1 of t plus c2 y2 of t. So basically we have the homogeneous solution. So L of yh equals 0. And just to note that L of y1 would be equal to 0 and L of y2 would be equal to 0. Because if you plug those two linearly homogeneous solutions into the left-hand side, it's going to produce 0 because they're homogeneous solutions. Now the goal now is to find a particular solution to L of y equals g of t. So we're trying to find a solution to the non-homogeneous equation yp. And what we're going to do is we're going to assume that yp of t has the form some unknown function u1 of t times y1 of t plus u2 of t, some other unknown function, times y2 of t. So we know y1 and y2, but we don't know u1 and u2. This is unknown function. And same thing here, u2, that's an unknown function. So our goal at this point is to figure out u1 and u2. So we will derive the functions, or we will find the functions u1 of t and u2 of t. All right, so what we're going to do is, if we have two unknowns, we need two equations. So note, if we have two unknowns, we need two equations. Right, to solve for two unknowns, we need two equations. So we're going to come up with some equations based on deriving yp and then substituting yp and yp prime and yp double prime into our differential equation. So yp, so here this begins the derivation of what u1 and u2 are. So yp we know is u1 y1 plus u2 y2. So yp prime be equal to, well, that's actually two products of functions of t added together. So if I'm going to differentiate, I have to do a product rule for both u1 y1 product and u2 y2 product. So that's going to be u1 prime y1 plus u1 y1 prime plus u2 prime y2 plus u2 y2 prime. Now what we're going to do is we're going to get our first equation right here kind of artificially by imposing that u1 prime y1 plus u2 prime y2 is 0. So we now pick our first equation to be u1 prime y1 plus u2 prime y2 equals 0. So that actually takes two terms out of yp prime. So yp prime now, after we impose that condition, is going to be u1 y1 prime plus u2 y2 prime. So we'll just call this first equation right here equation 1. That's our first equation. Kind of artificial, but really just to simplify yp prime, because our second derivative would be really nasty if we had to differentiate that. So it's really simplifying yp prime, and it's eliminating derivatives that we're not really going to have any use for, like u1 prime and u2 prime. Like those are not really going to show up anywhere in a nice way, so we'd like to get rid of them. So that's one equation. Now yp double prime can differentiate again and get u1 prime y1 prime plus u1 y1 double prime plus u2 prime y2 prime plus u2 y2 double prime. Again, just doing a product rule for each of those products. And now what do we have? We have yp, yp prime, yp double prime. So now substitute these derivatives into L of yp equals g of t. Let's see, so that's going to be, first one is yp double prime, so that's going to be u1 prime y1 prime plus u1 y1 double prime plus u2 prime y2 prime plus u2 y2 double prime, and that's yp double prime, plus p of t times yp prime. Well, yp prime was u1 y1 prime plus u2 y2 prime plus q of t times y, and that was just u1 y1 plus u2 y2 equals g of t. Now let's factor out some like terms. What do I have? I have u1 y1 prime, u1 y1, or u1 y1 double prime, u1 y1 prime times p, and u1 y1 times q. So what we're going to do is we're going to write u1 y1, u1 prime y1 prime plus u1 times y1 double prime plus p of t y1 prime plus q of t y1. And also we have, let's see, going to write plus u2 y2 prime plus, and then we can factor out, let's see, we have a u2, 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 so factor out u2. That leaves us with y2 double prime plus p of t y2 prime plus q of t y2 equals g of t. And I think I missed a prime right here on this u2. u2 prime, y2 prime in the middle, sorry. Okay, now, what's going on right here? This is really just L of y1. And this right here is really just L of y2. And what do we know about L of y1 and y2? Well, that's equal to 0. Both of those are 0. So really, we just get this last equation, u1 prime y1 prime plus u2 prime y2 prime equals g of t. And that is actually going to be our second equation. So this is equation 2. So got two equations, and it was u1 prime y1 plus u2 prime y2 equals 0. And now I've got u1 prime y1 prime plus u2 prime y2 prime equals g of t. So the unknowns are u1 prime and u2 prime. So to solve the system, we're just going to use Cramer's rule. So we just use Cramer's rule to solve. So that's going to be u1 prime equals 0g of t y2 y2 prime over y1 y2 y1 prime y2 prime, and u2 prime is going to be y1 prime and 0g over y1 y2 y1 prime y2 prime. What is that denominator? That's really just a Wronskian. So this is really just a Wronskian. So denominator is just the Wronskian. So in reality, this is really where you start your solution, right? After you start the particular solution, you would jump straight to this point, set up these determinants, and solve for u1 prime and u2 prime. And then just integrate to get u1 of t and u2 of t. So the steps would be first solve for YH equals C1Y1 plus C2Y2. Step 2, set up determinants for U1 prime and U2 prime. Integrate to get U1 and U2 for form general solution, which would be y equals C1y1 plus C2y2 plus U1y1 plus U2y2. And then step 5, solve for C1 and C2 if you have initial conditions, if given initial conditions. So this up here is basically the end of the derivation. And then this is the general variation of parameters steps that you need to follow. Variation of parameters. Solution method. Cool. Quite a derivation. And I have been known to throw a bonus question sometimes, from time to time, on the second exam that ask you to derive variation of parameter solution. But I don't think that's going to fly with Dr. Ming. He may or may not go for that. So anyway, might think of something else to put a little bonus in there somewhere. So any questions? I know the derivation, probably you were bored. You were waiting for it to be over so you could just smash that like button. Because you're like, oh, thank God it's over. Any questions? Let's look at some examples. YP double prime minus 3y prime plus 2y equals 1 over 1 plus e to the negative t. 1 over 1 plus e to the negative t. So, man, gotta solve for yh first. So solution. So first thing, solve for yh. yh of t. And that is going to be m squared minus 3m plus 2 equals 0. Let's see if we can factor that one. I think we can. M minus 2, m minus 1 equals 0. So our yh of t is going to be c1 e to the 2t plus c2 e to the t. And so we'll call the first one e to the 2t, we'll call that y1. The second one we'll call that y2. All right, so that's our homogeneous solution. Now, step 2, set up the determinants. u1 prime is equal to 0g y2 prime over the Wronskian. So what's the Wronskian? Just calculate that really fast. It's going to be y1, y2, y1 prime, y2 prime equals, let's see, e to the 2t, e to the t, 2 e to the 2t, e to the t. That Wronskian turns out to be e to the 3t minus e to the 3t minus 2 e to the 3t, which is negative e to the 3t. So that's going to be 0g, or 0, 1 over 1 plus e to the negative t. Over here it's e to the t, e to the t, all over negative e to the negative 3t. So that's u1 prime. So u1 prime is going to be e to the t, let's see, negative, right? Negative e to the t over 1 plus e to the negative t over negative e to the negative 3t. Man, what can we do? The negatives cancel, and the negative 3t can move all the way up to the numerator, so that's like e to the, make sure I'm not screwing this up, it's like e to the 4t. Make sure I haven't made a mistake somewhere. How did I get negative 3t right here? That's a problem. It's positive 3t in the denominator. Okay. There we go. Now we're good. So this is going to be, let's see. I can move it up and I can say e to the negative 2t over 1 plus e to the negative t. Let's do a little algebra there. Let's see. Is that where I want to be? I think so. I think so. So we'll break this up as e to the negative t times e to the negative t over 1 plus e to the negative t. And so u1 of t will be the integral of e to the negative t over 1 plus e to the negative t dt. And to integrate this, yes, thank you, Tess. Correct, yeah, yellow, right. I messed up that -3. So what I'm going to do is say that I'm going to do a u sub, u equals 1 plus e to the negative t. So basically the denominator is going to be my u. And then e to the negative t, I can rewrite that as u minus 1. And then again, du, I can write as negative e to the negative t dt. So this whole u sub is going to be integral, let's see, e to the negative t dt, that's negative du. And so this is going to be u minus 1 over u times negative du, which is going to be negative integral 1 minus 1 over u du, which is negative, and then u minus natural log absolute value of u. And then substitute what u is, so it's back to negative 1 plus e to the negative t minus natural log absolute value 1 plus e to the negative t. So do a little u sub there, and that is u1 of t. Now I have to get u2 of t. So u2 prime is going to be y1 prime 0g over the Wronskian. That's going to be e to the 2t 2e to the 2t 0 1 over 1 plus e to the negative t over e to the 3t. That's going to be e to the 2t over 1 plus e to the negative t over e to the 3t. Algebra says we can reduce that to e to the negative t over 1 plus e to the negative t. Integral is going to be a lot easier. u2 is going to be the integral of e to the negative t over 1 plus e to the negative t dt. I'm going to do a u sub again. U equals 1 plus e to the negative t. And then du equals negative e to the negative t dt. So this is going to be negative du. So this will be integral 1 over u times negative du, which is negative natural log absolute value of u. And we can write that as negative natural log absolute value 1 plus e to the negative t. And we could use log rules to say that's natural log 1 over 1 plus e to the negative t. So then we can form our general solution. Just zoom out a little bit so I can keep track. This is U1 right here. This is U2. Let's see. U1, Y1 be equal to negative 1 plus e to the negative t minus natural log 1 plus e to the negative t. And times y1, which is e to the 2t, which is equal to negative e to the 2t minus e to the t plus e to the 2t natural log 1 plus e to the negative t. And of those two, or of all those, what's duplicating our homogeneous solution is actually just this term right here. It's the only term that doesn't duplicate y sub h. The only term which does not duplicate y sub h. So that's the only real new term for our solution, because we already have c1 e to the 2t plus c2 e to the t. So we only keep the terms that do not duplicate y sub h. So only keep terms that do not duplicate y sub h. So also ut or u2 y2 be equal to e to the t natural log absolute value 1 over 1 plus e to the negative t. And that doesn't duplicate yh. So then our general solution, y of t, is going to equal c1 e to the 2t plus c2 e to the t plus e to the 2t natural log absolute value 1 plus e to the negative t plus e to the t natural log absolute value 1 over 1 plus e to the negative t. And basically this part is our yp, the part that doesn't duplicate yh. And that is our general solution. And that's our general solution, so we don't have any like initial conditions. If we did, we'd have to shoot. Ronskin's negative. You're right. Thank you. So let me see what changes. Negative, 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 positive. So yeah, this should not be in the denominator. 1 plus e to the negative t. So u2, this should just be 1 plus e to the negative t. Yep, thanks. 1 plus e to the negative t. Thank you. So yeah, all those changes are in white. Thank you. Good catch. If we were in class, I'd throw you a piece of candy. Good catch. Man, good stuff. Good stuff. I do one more example. do one more example here. And it'll be something like y double prime plus y equals tan x. And this will assume that x is between 0 and pi over 2. Basically a portion of the domain of tangent. So solution, step 1, find YH of x. So this can be y double prime plus y equals 0, m squared plus 1 equals 0. So that's m equals plus or minus I. So YH of x is going to be C1 cosine x plus C2 sine x. Now I've got our y1 and our y2. Step 2, set up the determinants. U1 prime equals 0 tan sine x cosine x over the Wronskian, and U2 prime equals cosine negative sine 0 tan over the Wronskian. What's our Wronskian here? Our Wronskian is going to be cosine x sine x negative sine cosine. It's actually just 1. Cosine squared plus sine squared, basically. So let me write that out. That's just going to be cosine squared x plus sine squared x, which is 1. So really, the Wronskian is kind of irrelevant in the denominator. It's just 1. So that tells us U1 prime is going to be negative sine x tangent x, and U2 prime is going to be cosine x tangent x. So U1 prime is going to, or U1 is going to be the integral of negative sine x tangent x dx, and U2 is going to be integral of cosine x times tangent x dx. All right, so now how do we integrate these two? Well, a good strategy usually is to change tangent to sine and cosine if there's already like a sine and cosine that you can't turn into secant or cosecant. So we'll change it to everything in terms of sine and cosine. So it's going to be integral negative integral sine squared x over cosine x dx. And this is going to be over here, U2 equals cosine x times sine x over cosine x dx. Not too bad actually on that one. The sines are going to, or the cosines are going to cancel. That's easier. The first one, oh man, what do you do? What do you do? Let's see, we could write this as negative integral 1 minus cosine squared over cosine squared. Just a little trig identity, Pythagorean identity. And then over here, U2 is actually just integral of sine, which is cosine. Don't have to do plus c's because you're multiplying by y1, and if you do y1 times the constant, it's part of the homogeneous solution. So no plus c or no plus c's are needed. The negative sign can change this to be integral cosine squared x minus 1 over cosine squared x dx. And that's going to be integral of 1 minus secant squared x dx, which is really just x minus tan x. So U1 is x minus tan x, U2 is cosine x. So that tells me that yp is going to equal x minus tan x times cosine plus cosine x times sine x. I've screwed up somewhere, right? Again, man, it's just not my day, is it? Not my day. What did I screw up? I screwed up right here. How did I screw that up? I screwed up because I somehow just arbitrarily put a cosine squared down there. It's not cosine squared, it's just cosine. Oh, just not my day. Because I don't know what's going on. Lost my mojo. Let's do this as cosine squared minus 1 over cosine dx. This is going to be integral of cosine x minus secant x dx. There we go. Now we're talking. Let's see. This is going to be integral of cosine is sine minus integral of secant. Integral of secant. Anybody remember? There's usually one person who remembers integral of secant. It's that weird trick you have to multiply top and bottom by the same thing, and the thing that you multiply top and bottom by is secant plus tangent. Makes it a u sub, and then you can get natural log absolute value secant x plus tangent x. And that's u1. Okay, sorry about that. Yp now is going to be let's see, sine x minus natural log absolute value secant x plus tangent x times cosine plus cosine x times sine. And golly, man, just making tons of mistakes. I'm so sorry. This is a negative cosine, right? Integral of sine is negative cosine, so that makes this a negative right here. My goodness. Rough one. It's a rough one. It's a rough one. So this is going to be sine x cosine x minus natural log absolute value secant x plus tangent x minus cosine x sine x. So these cancel, and we get just negative natural log absolute value secant x plus tangent x for yp. And that means our general solution, y, is going to equal y of x. It's going to equal c1 cosine plus c2 sine minus natural log absolute value secant x plus tangent x. And that's our general solution. And if we had initial conditions, we could plug those in, solve for C1 and C2. Oh my gosh, another mistake. I forgot to multiply by cosine. My gosh. Okay, I think I'm gonna call it a day because this is rough. I gotta stop before I lose my mind. I am so sorry. It's a rough one. Okay, it happens. Need to get some more sleep, I'm sure. Goodness. All right. Any questions? If not, we'll call it a day. I gotta stop. This is it's killing me. Hang out for a few seconds, see if anybody has any questions. If not, you're free to go. Peace out. See you guys on Thursday. We'll do 4.7 and 5.1. So Have a good one. Unless you got some questions, I'll talk to you. Yeah, thanks guys. Hey, you know it happens. So try to have compassion, whenever you miss something on the exam. There you go. Can't say the same for Dr. Ming, but yeah, I'll double check on the homework, make sure everything's up. Cool. All right, see you guys later. Y'all have a good one.